said he's going to switch gears, and he's going to tell us how.
Yeah. So I'm going to talk about something slightly different from the last hour. This time, the work that I'm going to tell you about is really being done in collaboration with Toan, who's still my postdoc. Greg Morrison was my student, currently a postdoc in Harvard, and this guy was my student, now is a professor in Korea. The history of using force at the single molecule level in the context of biophysics is only 18 years old, I think. The very first experiments that were done were by Carlos Bustamante, where he, while he was still in Oregon, measured the force extension curves for double-stranded DNA and showed that the force extension curve going from, I think I don't have data on this, but I have experimental setup, from 0 to about 65 piconewtons could be quantitatively fit by the exact analysis that you might get. It's almost exact analysis from a Wormlike chain model. Since then, force has been used in many, many different contexts, and after some introduction, I will talk to you about a very specific set of experiments on using laser optical tweezers to fold and unfold using constant force hairpins. In particular, I'll show you data and some analysis on RNA hairpins. We now know that force is everywhere in biology, cell crawling, and how that's molecularly tied to cytoskeletons. There are lots of I think that you heard from on the Friday afternoon session was devoted in some sense to mechanical sensing at some level. It's most people will think without force there's no biology, and et cetera, et cetera. So history, as I recall it today. In the material world, of course, this is not unknown, because this morning also you heard about stress tensor and so on and so forth in material context. Biophysics, this is the first experiments as far as I know. In proteins, it is Hermann Gaub and Carlos Bustamante reported, and there's another paper as well. And that person, Simmons, seems to have dropped out of the game in 1997. Coincidentally, all of them were using force to unfold Titan, which is a very, very large protein consisting of many multi-subunits of immunoglobulin domains interspersed with polyampholytes. In the theory, in fact, he was way ahead of his game, and I'll describe, I think, a bit of these results. My good friend Phil Pincus in UCSB, this is the very first paper he wrote on polymers, and in it was introduced the concept of blobs. There was a paper by Marshall Fixman in 1973, which described force extension curves for a Wormlike chain model, which formed the basis of analysis by Marco and Sigia. And then there are other things. So this is what I want to do in this first part, and then I'll talk about a specific example. So there are many kinds of polymers, and the response to force varies depending upon what sort of polymer you're considering. Some of them are applicable to some proteins, some DNA, some RNA, and there are questions as to why that is the case, and one wants to understand that some theoretical way. So I'll review some basic polymer physics, the measurements of force climb for RNA, this constant force, and how to extract these landscape from experiments. So these must have been some kind of experiment. This is sort of the setup that is used by this is not the magnetic tweezers. So you basically have a cover slip in which you have DNA adsorbed, and you have a magnetic bead. There are some better experiments that I'll show you before, and then this is under laser trap. You can either flow some fluid, or you can use a micropipette to suck it and that transmits some force, and then you measure what the extension is through some electronic gadgets. So this is typically what you get for, and incidentally, there are very beautiful experiments with, Willem and I were talking about Ninka Decker. She's doing some really gorgeous experiments applying torque to DNA, and these were reported a couple of years ago. So this is a force extinction curve. I think it's from Carlos's lab, and you see as you increase force in this direction, the extension of the molecule actually increases. Okay, the typical force ranges that you'll encounter today are of much less than 100 piconewtons, but somewhere between 1 to about 15-20 piconewtons. The spatial resolution is much better than what is reported here. Maybe it can go up to 1 nanometer. Yeah, this is a slide from my student, and he wanted to tell you what kind of forces you look at. So apparently this is the amount of force required to undo our hair, but that's about 1,000 newtons or something. But anyway, this is a force of piconewtons. The nanonewtons of this force case we're going to look at. You need about Newton or so to break bonds. I don't know how many there are. This much to break bonds, and steam engine is I don't know, mega newtons. So this is from somebody else. Okay, so we're talking about piconewtons, and KBT is 4 piconewtons nanometers. So that's a scale that you should remember. I'll come back to this experiment, but let me describe this experiment to you. These are the first experiments done on single molecule RNA. So this is an RNA. It's just a garden variety RNA from tetrahymena ribozyme. It's called P5AB. There are paired helices A and B. This is done in the absence of magnesium, and so the only structure that you have is secondary structure. And they also reported experiments on these two, but we'll just focus on this. The way the experiment is done is that the 5' and 3' ends of this RNA are attached to a handle, and the handle is typically a DNA handle. So this is the construct. So you have the hairpin of interest. You have RNA and DNA, RNA-DNA hybrid handles, and there is a biotin at one end, and therefore there's specific recognition. You can trap this by laser. You can suck on it, transmit some force, and the force typically propagates on a time scale that's much faster than the time scale in which the RNA hairpin actually goes between the folded and unfolded state. 1 to 100, this is 1 nanometer already. So the force extension curves that you see typically are increasing force this way. You're pulling this at a loading rate of 1 piconewton per second. You see a force, this is a blue, is when you're pulling in on one direction, and there's a blip in here that corresponds to some things that happens in the RNA hairpin. And then this is another extension. These two extensions correspond to extensions of the DNA alone. One knows this for sure because quantitatively one can predict what the force extension curve for the DNA is, and so the blip must tell you something about the state changes here. We'll see later on, in fact, when you do constant force experiments and constant force simulations, these corresponds to folding and unfolding of this RNA hairpin. It's rips and unrips, reforms. And the green is what happens when you actually decrease the force, or is the other way around. There's very little hysteresis here, but if you increase the loading rate by a factor of 10, you see some hysteresis in the folding and unfolding. So these are the kinds of curves that you want to think about, although nowadays, almost all experiments, I shouldn't say almost all experiments, many experiments are done at constant force as opposed to constant loading rate. The other mode in which experiments are done is using AFM, in which you have a surface onto which your polyprotein is attached. This is just a bunch of proteins, say ubiquitin, that's joined together. And then you have a cantilever beam, and then you bring the cantilevered beam onto the surface. It'll grab onto the protein, and then you withdraw the cantilever beam, and then it exerts a force on this construct. There's a deflection, and through optical tweezers, to optics, you can detect how much the deflection there is, which then tells you what the force is, and you can then get force extension curves. The typical force extension curves that were first reported in '97 go like this. It increases, it drops, increases, drops, etc., and one can now quantitatively explain these things. These correspond to domain by domain unraveling of each of these constructs. So in this case, you have 3 constructs. So if you had done this experiment on this particular construct, you'd have seen 1, 2, and 3 sawtooth patterns. The force range here goes about 1,000 piconewtons or so. The loading rate here is about a factor of 1,000 larger than laser optical tweezers, so it's of the order of about 1,000 piconewtons per second. So you're pulling it much harder, and because you're pulling it much harder, you need much higher forces to unravel this. And in fact, in a one-dimensional theory, you can work out how the most probable force that you must exert on this construct, how does that scale with the loading rate itself. And to first approximation, it scales logarithmically with respect to the loading rate. So these are the 2 modes in which you do these experiments. In both of them, you're actually pulling at some loading rate, one which is very small in the case of laser optical tweezers, one which is much larger, and you're getting force extension curves. And later on, I'll tell you about constant force experiments. So some preliminaries here. So I already said the KBT is 4.1 piconewtons nanometers. Chemists would say it's about 0.6 kcals per mole. And the question is, how do you understand this force extension curves? And that's what happened after these experiments are announced in the 90s. And although it's not fully understood how to describe these force extension curves, especially when you go to sequence-specific interactions, like in DNA, there are still lots of work to be done. But from a polymer perspective, one can globally describe how these things work. And there are 3 popular models that are used. One is a freely jointed chain. I'll describe that in a second. There's a Wormlike chain. And very seldom used is a self-avoiding walk. How does a self-avoiding walk respond to force? And that displays a different scaling behavior, which is only shown to hold good for single-stranded DNA molecules, I think last year. Okay, let me see, there are some, oops. So let's consider a Gaussian chain. So you just basically have a chain, no interactions, joined by springs, and it's very long. So we know that the probability of the end-to-end distribution is simply given by a Gaussian. This is the number of beads. This is the Kuhn length, if you wish. The end-to-end distance scales as 10 to the power 4.5. For a self-avoiding walk, this is the scaling, and we already saw this in the last talk, in the last hour, that it goes as R and 0.6. Okay, and then this is the end-to-end distribution function for a self-avoiding chain. Let me see. Okay. This does not look so good. So what's a freely jointed chain? Freely jointed chain is just thus. You traverse in space, you take a Kuhn length, and you can go in any direction. At each joint, the chain can rotate anywhere you want. And then you trace the unit vector that goes from the beginning, the first monomer, to the nth monomer. This is one conformation of the chain. The distance between that is R. You repeat this experiment. There's only entropy here, and then you'll get a distribution. And this is an example of a distribution of freely jointed chain. And the freely jointed chain, the distribution function looks basically like a Gaussian chain. The average end-to-end distance scales as square root of n times is LK, which is roughly speaking the monomer length. So, succession of rigid bodies, how is this okay? In fact, you can do this calculation almost analytically. Not almost, you can. Okay. You will hear the term of entropic elasticity. What does that mean? In the absence of tension, in the absence of force that you apply to the ends of the molecule in fact likes to be completely random, because it can have the largest number of conformations that way, or minimize the entropy. And so it favors disorder. And in that conformation, R squared for the freely jointed chain goes as square root of n. So that's what you see. But now when you stretch it and you keep applying force, you straighten out various parts of the segments of the molecule until you reach a rod state, and you're fighting against this entropy that it likes to have by applying this external tension. And that's why these force extension curves are called entropic elasticity. If you take the derivative of that, you'll get a elastic constant, and for that reason, these things are called entropic elasticity. Force tends to reduce order, and the natural conformation tries to increase disorder. increase order and decrease disorder. Okay, let me see. Oops. Okay. So this is a freely joined chain, and I think this people given as homework actually in a usual statistical mechanics class that calculate the extension along the force direction for this freely joined chain, and this is sometimes or often referred to as a Langevin function. And if you look at the force as a function of extension in some suitable reduced units, it goes linearly, just like Hooke's law, as a function of force, and at large forces it goes as 1 minus inverse of F. So at high forces, for a freely joined chain, you expect a behavior as 1 minus 1 over F. So if the force extension curve scales as 1 minus 1 over F, you know that it must correspond to a freely joined chain, a large forces. It turns out that if you do experiments in cellulose is this repeated many, many times, and the force extension curve can be completely described by the freely joined chain. You take some initial guesses, and these are the best fit values, and the persistence length is about 0.885 nanometers. The contour length is this much, and the goodness of fit is pretty good. And these guys showed, unlike the DNA, double-stranded DNA, that the force extension curve is well described with a freely joined chain. Not so for the DNA. So you can do the same kind of calculations for DNA, and this is the force extension curve, and if you make the freely joined chain approximation, you basically get a persistence length is way off, the contour length is way off, and the curve is just no good. So the freely joined chain cannot describe the force extension curves for DNA. Okay, so one wants to understand what's going on here. Let's see. Okay, so this is a Wormlike chain. It has just got a bending energy term in a functional integral sense. If you describe this curve as a contour of one-dimensional contour in a three-dimensional space, the bending energy goes as 1 over the local curve, which is squared, and then you can sum over all the paths, and you can apply a force. You can calculate the force extension curve. Numerically, it's equivalent to a Schrodinger's equation on a sphere, and you can solve that numerically, and if you do that and you make a fit, this is what you get for the force extension curve, and this really fits the data extremely well. The characteristic of this Wormlike chain model is at small forces is of the order of a piconewton or less. The force, in fact, the extension scales linearly with F, but at very high forces, you can show, this has got to be square root of half actually. The force extension goes as, x goes as 1 minus f to the minus half. So this is not 1, it's half. You remember in the Wormlike chain, in the freely joined chain, it was 1 minus 1 over f. This is 1 minus 1 over f to the minus half. And therefore, if you observe force extension curves asymptotically at large values of force, which in the DNA case turns out to be about 65 piconewtons, above that, there's something interesting that happens, which is called the overstretching transition, that involves some fundamental conformational changes in the DNA that I won't describe. But at 65 piconewtons, this is how the force extension would go, except this has got to be a 1/2. So these are the two cases: freely joined chain and whoops. Okay. So what is a persistence length? So the standard definition of persistence length is that if I consider a polymer as a curve, so DNA as a curve, of course it's got a thickness that you should really worry about, as a curve, and this is a contour length along this, and you have a local tangent vector here, another local tangent vector here, and you calculate the tangent-tangent correlation function, which is just u hat s and u hat s prime, and the distance s minus s prime is s, cosine of that. That'll go as e to the minus s over a characteristic length, and that characteristic length is the persistence length. That's a standard definition of persistence length, and is related to the stiffness of the polymer, and we already gave some examples of this before. For protein, it's about 0.5 nanometers. Single-stranded DNA is about 1 nanometer. Double-stranded DNA is about 50 nanometers. In sodium chloride, it's actually much smaller in the presence of magnesium and so on. And microtubule is about several micrometers. Actin is about 1 micrometer, and so on. So the persistence length can vary from very small numbers to very, very large numbers. Okay. is DNA a Wormlike chain? So if I now do the same fit as a Wormlike chain, the little extrapolation formula, force is a function of extension, and you get very good results for the persistence length. It's an excellent quality fit. These are basically the residuals, which are very small. And so we now know these are all fits from this guy's paper. I think it's Steve Block, actually, as far as I remember. But anyway, and it fits extremely well. The reason why some molecules fit by Wormlike chain, some molecule by freely joined chain is explained in this paper, and I don't think I'm going to explain that here, although I've not really fully seen this talk since the last time I gave it. So, yeah, I'm not going to explain this. Okay. Oops. Can you guys see this at all? Huh? These are the results for single-stranded DNA and RNA, and this is a lovely experiment that was done by the French group Vincent Croquet and David Ben-Simon for single-stranded DNA. And the elasticity, this is, I'm sure you can see this. This is a force as a function of extension. The force goes from about 1 piconewton to about 1,000 piconewtons. And the elasticity, which will simply be the derivative with respect to these guys, depends upon how much force you actually exert on the system. In some regimes, as Wormlike chain, at very large forces is like a freely joined chain, and the reasons why the very nature of the response of the polymer varies with force is explained in this article that I don't want to get into. And so one of the things we showed is universally, no matter what system you're looking at, as long as it's very large, at very large forces, in fact, you'll always get freely joined chain, and in intermediate range of forces, you can describe the elasticity by Wormlike chain. So this is another stuff involving polyelectrolytes. I'll leave it alone. So the various stretching regimes that one can actually think about. Imagine you have a protein or a globule. This dashed line, below this dashed line, there are specific forces, enthalpic forces, that stabilize this particular structure or this particular structure. So here, the elasticity is not any more entropic elasticity. You have to overcome the forces of cohesion that hold the strands together or the strand and the helix together. So you cannot use polymer theories to describe what happens to the force extension curve in this regime. Above some regime, when you stretch the molecule enough such that the cohesive energies, so that's a characteristic force where the cohesive energies divided by the extension balance each other, then you're basically fighting only entropy. In that case, once you cross this line with this value of force, initially it behaves like a self-avoiding walk in which the extension scales as f to the power of 1 over nu minus 1. That nu is the same Flory exponent that we described before. If I plug in numbers, you get the so-called Pincus regime or Pincus-Blob regime in which extension goes as f to the 2/3. Okay? It's no longer linear like in a Gaussian. So that's the first thing that happens. Above this regime, the Wormlike chain behavior takes over, and the extension goes as 1 minus f to the minus a half. That's characteristic of DNA, for example. And then if you keep increasing force still further, you get to the freely jointed regime, and therefore in this, if you wish, could be thought of as a universal phase diagram for polymer systems that are subject to force. And a given polymer, a given biopolymer like cellulose or RNA or DNA or double-stranded DNA, where they fall in this will depend upon what kind of force you're using and what kind of extensions you have. And so you have to worry about, and that in turn is determined by the persistence length of the chain. Because the prefactors that go in there are determined by essentially the persistence length. Okay, so that's a polymer introduction to how to think about these sorts of experiments. Now, the interest in this field is huge because you can subject the molecule, a protein or RNA, for example, to force. It's another probe, just like temperature was and denaturant was, and then look at how it responds or how it unfolds. Just like the refolding itself is dependent upon the topology of the folded state, the unfolding upon force also depends upon topology, and therefore it's legitimate for you to ask, what are the pathways that a molecule, when it's folded, undergoes when subject to force en route to the unfolded state? That kind of experiment, that kind of analysis cannot be done using experiments alone. Experiments give you only two kinds of information. One I've shown you before already, which is force as a function of extension. The other I'll show in a second, in a little while, which is the fluctuations in the end-to-end distance of the molecule as a function of time when you subject the protein or RNA to constant force. But what you really want to know is the entire folding landscape, the pathways that the molecule traverses from going from the folded to the unfolded state. These things were first done in a computer simulations by Klaus Schulten for I-27, which is one of the building blocks in the muscle titan. And what is being shown here, force as a function of extension, using what's called the steered molecular dynamics. There are a whole bunch of curves in here. This is the protein. These are the stretching velocities. They go from angstroms per nanosecond and to 280 to 0.08 angstroms per nanosecond. As I remember, this value is about 10 to the 7 or 10 to the 8 times greater than the velocities that are used in an AFM experiment. And therefore, this will be about 10 to the 6th or 10 to the 5th times. So in order to observe the unfolding event on a time scale of molecular dynamics simulations, which is, say, I don't know, 10 nanoseconds or something like that, you got to pull this at an extremely rapid rate. And therefore, the average peak forces that you require to unravel this IG27 range from about 500 piconewtons to about 1600 piconewtons, and the force in fact increases as you increase the rate at which you pull or the rate at which you load the system, and this is roughly speaking logarithmic. But because it's a molecular dynamics simulation, you can actually look at which parts of the structure actually come apart at what time, and thereby figure out the unfolding pathways, and that's what Klaus did for in 1998, and he's revisited this problem many, many, many times in the intervening years as the computer powers got better and better, just to convince himself, although I'm not persuaded, good friend of mine, but I'm not persuaded, that the unfolding pathways do not depend upon the velocity. That's really what he wants to argue, and this is not quite the case. But anyway, these were pioneering simulations that sets the stage for looking at very detailed way how various hydrogen bond patterns and things like that rupture. And these are not of interest to almost anyone in this audience, I'm sure. So yeah, okay. So that is just a bit of an introduction to the polymer models. But now I got to load a different talk actually. So, and I'll tell you about one specific problem that comes from experiments and how we are thinking about that. Open. I hope I remember the talk though. Okay. With that background that you now have and you understood all those things, let me tell you this problem. So I'm going to talk to you about unfolding a hairpin, the simplest system that could possibly exist either in a folded state, corresponding to the hairpin, or an unfolded state. This work is directly from this paper, and I may have time but not energy to tell you about the ribose switch, but if you want, you can read about this here. And then there are some further developments of force, which I'll mention a little bit, which appeared last year. This is our university. You remember this tree, right? Do you? This is the front of the university. So we are sort of down here somewhere, remember? Physics department is here. Right. And the administrators are having this building and more beautiful buildings on the left, even though they do nothing useful. And we have ugly looking buildings on the side where we're doing lots of useful things and bringing them the glory. This is computer simulations of fluctuations of this RNA hairpin, and I'll tell you more than you want to know by the time I'm done. This is the experimental setup, and I think I'm going to show this in some detail. Okay, so this is a bit of an introduction. Why do we want to know force? Unlike the protein folding problem, there's an RNA folding problem, and this RNA is it's called the tetrahymenorybozyme. This is a secondary structure map. The P stands for paired helices. In the presence of magnesium, it folds into the structure. Incidentally, this is the system from the tetrahymena is a bug in which Tom Cech actually showed that RNA itself can act as an enzyme when he was an assistant professor, which went on to get him the Nobel Prize. And since then, of course, we now know that there are many, many RNA molecules which can function as enzymes, including ribosome, which people call is a ribozyme. So RNA enzyme is called a ribozyme. This is, so these are all things that are not relevant. This I already showed you some things here. Okay. Carlos, in fact, does some of the very first experiments on many, many, many things. And this is the kind of experiment he first did on tetrahymenorybozyme. The great thing about this molecule is that you can subdivide this into domains. This domain in black is called the P5, P4, P6 domain. You can clip this and you'll get something called the P5 ABC domain. This is another P3, P8 domain. There's some peripheral domains. And it's known that this particular domain is the most stable. It's been crystallized. It was crystallized in 1996. This whole system has not been crystallized, so we do not know what the structure is. This is this is an experiment in which he measures the force extension curve with a loading rate of 3 to 5 piconewtons. This is Bibia Onoa who did these experiments, and this is the unfolding, and then this is the refolding. The various A, B, C, D, E, F, G, H are the order in which the subdomains actually unravel. That's not at all transparent from this one-dimensional curve, if you wish. All you know is the force versus extension. He can assign this to the unraveling of, say, the purple first, because he would do the force extension curve of each of the subdomains separately, and assuming that they are independently unfolding, he could go back and assign that initially this must have unfolded, and then next, and finally this black curve H, this domain in fact unfolds, and that's the most stable domain, the P4, P6 domain. So that way he could assign the unfolding event at this pulling rate, loading rate using this strategy. Very, very painstaking experiments. And Felix Rithot, David's colleague, in fact, is doing these sorts of experiments, as he told me yesterday, on anything that he can lay his hands on and pull, and this is the stuff that he, in fact, learned from Carlos's lab. Another way in which you do the experiments, from now on I'm going to shift to that, is the following. These are experiments that Julio Fernandez reported some years ago, using force as really a mechanism to trigger folding and unfolding. And these are gorgeous experiments as well. This is on polyubiquitin. By polyubiquitin, I mean ubiquitin strung together many times, say 8 times. Initially, you apply a constant force, and there's a feedback mechanism that maintains the force constant for some period of time. There's invariably some drift at some point that you got to worry about. And you completely unfold it, and unfolding takes place in the staircase. Each staircase represents unfolding of one particular domain in ubiquitin. At the end, when you apply long force, it basically fully unfolds. You essentially get a rod state, almost a rod state. Then you can quench the force to about 15 piconewtons. And the molecules in the subdomain start folding. And what you can measure is the extension of this construct as a function of time. And this is a folding trajectory that one can measure. And it comes back to about 120 it comes back to the fully folded state, and you know it's fully folded state because if you repeat then the fully folded unfolding experiment, that pattern should look exactly like this, and you see that's in fact the case. So he knows that the extension has reached the value corresponding to the fully folded state. And this is to show that in fact the force is roughly constant during the duration of this experiment. That's in fact the case. Now, in this paper that I told you that appeared last year, we suggested theoretically that you can do better than this. You can in fact use force pulses, just like NMR pulses, in which you quench the force for some period of time, which is not long enough the molecule to unfold. Then you increase the force, and then you repeat this force pulse many, many times for arbitrary durations in which you keep this at low force. And then you can use theory and experiments to get at the dynamics of reconfiguration of the compact states as the molecules are unfolding. Okay, so that's a story for another day. So the laser optical tweezer setup, and I'll describe this a few times, it goes like this. You have an RNA hairpin or a DNA hairpin. You have a hybrid handle. This is just the way we did the computations. And these are the two beads. And this bead is trapped in a laser field. And this bead is also trapped in another laser field. But then you can yank on this by micropipette and put it at constant force through a feedback. And that transmits a constant force across this construct of handles, RNA, and the handles. And what you really want to know from these experiments is not the landscape of the whole setup, but the landscape of this red piece in here. The dimensions are worth remembering. The RNA dimensions are about 2 nanometers. The bead is about a micron, say. The handles are the order of a micron long. And so the way you're really trying to do this experiment, it's inevitable to do this, is you're trying to get the weight of a human being by weighing the ship plus a human being, then the ship, and subtracting it out, and you want to know what the weight is, and that you have an analogous problem here. These are absolutely gorgeous experiments, and I'll show you some data, and therefore you really want to take this data very, very seriously and try to figure out, using polymer dynamics, how to deconvolute the motions of the beads and the handles, and then just merely get the landscape of the RNA hairpin, and that's the story, and then I'm going to tell you the rest of the 40 minutes or so that I have. These are back to the experiments. These are experiments that are published in 2006 in Science by Steve Block, and on an RNA hairpin. The extension, and by extension here I mean, extension here in an experiment means the distance between the two beads. So it will include the bead, the handle, the hairpin, handle, and the bead as a function of time. At a particular value of force, and that's a time trace that's shown here, and you can see in a duration of 15 seconds, this system of the distance between the two beads jumps from this value here to another value here. And it jumps more or less instantaneously, and you see multiple transitions. You know from statistical mechanics that this trajectory was long enough such that the system has explored all the conformational space, then ergodically sampled it. You can do a histogram of the various conformations using extension as the underlying reaction coordinates or the parameter, if you, in this case, if you wish, and look at the probability of this large extension that will be identified with the unfolded nature of the DNA hairpin, and a small hairpin, a small distance, which corresponds to the folded state. And roughly speaking, you have a bimodal distribution. Okay, so unfolded state, unfolded state. The area under this curve is roughly equal to the area under this curve, although it doesn't quite look like it. This is a bit fatter, and this defines a midpoint of the transition. Therefore, at this value of force, which is about 15 piconewtons, I recall, the system, which will eventually be attributable to the DNA hairpin itself, exists with equal probability either in the unfolded state or the folded state. So then the free energy profile in terms of this extension, for the time being, I will later on define 3 extensions, and this extension is the equilibrium free energy profile, which is a logarithm of the probability, and that tells you it's bimodal, and you can figure things out. from the same trajectory, we can also determine very easily the dwell time in the folded state or the dwell time in the unfolded state, and this is basically the duration of time it sits in this low extension and the duration of time it sits in the upper extension, and you can get an average hopping rate between the low extension and the high extension by simply looking at this trajectory. And if it's a single exponential, it must mean the distribution of this hopping time, distribution of this dwell times is going to be Poisson distribution, and you can get an average folding time from that. So from this single long trajectory, subject to constant force at one value of force, which in this case is the midpoint, where you see a number of transitions, you can determine both the equilibrium properties and the hopping rate at that particular value of force. Fantastic experiments. This is what makes the experiment even better. So this is an experiment by Woodside and company in 2006. This is the kind of curve that you saw. They were looking at DNA hairpin, and they were not looking at one DNA hairpin. They looked at 4 DNA hairpins, and the DNA hairpins differed by the GC content of the hairpins and the location of the GC. So this red, yellow, I guess, is the location of GC. In this hairpin, all the GC were close to the ends, away from the loop, and this is the force extension curve you got. From the hopping time, the unfolding time, you can use, this is so-called Bell model, the location of the transition state from, say, folded, there's a transition state, and then past the midpoint, that's the location of the transition state with respect to the folded conformation. Likewise, from the folding time, you can get the delta X F double dagger. They wanted to show these are two-state systems with R as an excellent reaction coordinate, the extension. So the distance between these two basins of attraction, say, is delta X. If this were strictly two-state, this delta X must be a sum of this number and the corresponding value for the folded transition state. And that's what is shown here. The distance is in nanometer. This is a transition state in base pairs from the folded state. This is delta XU double dagger, delta XF double dagger. In all these cases, if you add these two numbers, you'll get the green curve, which is the distance between these two basins of attraction, and therefore it must be that the RNA hairpin is undergoing a two-state transition, either it's in the folded state to first approximation anyway, unfolded state, at this particular value of force, and that the location of these transition states can be varied at will by sequence composition and where you actually put the GC content in this particular case. So the moral of the story is this landscape is sensitive to the sequence, and you can control the folding basically by placing the GC base pairs at various positions along the stem. Fantastic experiments. So it should be the end of this story. But the experiments raise a number of questions, and I'll try to answer a few of them. The experiments are not done directly on the DNA hairpin. I have these accoutrements to which I'm attaching this. I have the bead, I have the DNA, and I have this, I have the hairpin. So the first question is, how do the handles change the equilibrium free energy profile and the dynamics of the hairpin itself? The fact that I'm saying it's an RNA hairpin is because that's what we use, but the same considerations hold good for the experiments themselves. How does the handle length and stiffness affect these properties? And then, because this is you guys are all brilliant physicists, and I'm just a chemist, right? But I'll tell you a toy model in which one can do analytic calculations and then capture the essential physics. And the most important thing is the experiments really can give you reliable answers only at the midpoint of the transition. Midpoint, I mean the force values which are of the order. I don't see any force values here, happily. At or 15 piconewtons. So, but you really want to use those measured values at the midpoint and see if you can say something about the kinetics and thermodynamics at other values of force as well. Otherwise, the experimentalist has to do this experiment many times at various values of force, and as you go away from the midpoint, the number of transitions that you make will become smaller. In other words, and this is an important point, so maybe. So at this midpoint of the transition, you see a number of midpoint, you see a number of transitions. But if you go to very low values of force, you'll be mostly pinned here. And if you go to a very high value of force, you'll be mostly pinned there. The trajectory will no longer be ergodic, and you no longer can make these estimates of the folding times, et cetera, et cetera. And therefore, what you really want to do is take these lovely trajectories from Steve and then use theory to say something about other things, and that's what I'll show how it comes about. But still, even after I'm done in about 30, 40 minutes, there are other problems that remain that we're still working on at this point. Okay. First, for those purposes here, let's think about a simpler concept by looking at the bead dynamics. So I have this construct, a bead which is trapped in here. I'm trying to pull this. This is going to resist this. There's a trap has got a stiffness associated with this. There's a relaxation time associated with the trap, which is simply given by the friction coefficient by the spring constant. This gamma the gamma is appearing everywhere, right? Surface tension, this susceptibility exponent, and the relaxation rate. Everything is called this gamma. I should change that, I guess. The gamma is 6 pi eta. This is Stokes-Einstein. The bead is about 1 micron. Eta is 1 centipoise. The the strap stiffness is about 1/100th of a piconewton nanometer, to which is attached the handles, which is typically 0.1 piconewton per nanometer. That's DNA handles. And therefore, if you compute this guy, the relaxation times are of the order of 1 millisecond. If you look at the hopping times, they're about 0.1 to 1 second, and therefore, on the time scale in which hopping is taking place, these numbers are much greater than the relaxation time of the bead. And so the first approximation at FM, I'll neglect the motions relaxation associated with beads. Eventually, you really got to not only worry about that a little bit because the corrections are detectable, but you also have to worry about the hydrodynamics associated with that. And there's a much fuller theory that we have developed, but that's a bit complicated that we don't need to, I'll not worry about it here anyway. Okay. By linkers, I mean the handles, the DNA handles, and how does it affect the landscape. To do this, we're going to do this initially some simulations on the computer. We're going to create a hairpin. This is called a P5GA hairpin. It's an RNA hairpin. Its NMR structure was determined about 10 years ago by Nacho Tinoco, who is a good friend and collaborator and postdoc mentor of Carlos Bustamante. And this is the sequence of this RNA hairpin. So let's see how we do the calculations. The calculations are done by some simple models that we've developed over the years. For the purposes that I'm telling you, this accuracy of these models is not relevant because I'm talking about proof of principle in terms of the effects of the handle dynamics on the RNA hairpin. So 22 mer hairpin, much smaller than the ones that Steve actually did experiments on. They're stimulated by stacking. These are all well known. So the great thing about computers is I can do this calculations directly on the hairpin without attaching anything. And that will be the exact answer, so quote unquote, right? That's what I'm trying to reconstruct from measurements. Simulations show that, in fact, at midpoint of the transition is about 15 piconewtons, and this we reported earlier. And we know this because we've done this very carefully for this model. So, and now, all these curves that I'm showing you, there are no handles associated with them. They're exact answers. And this is the midpoint of the transition. This is the extension between the 5' and 3' of these ends of this hairpin as a function of time. And you see, it sort of looks like the experiment. Although this is a smaller system, there are some finite size fluctuations involved here. I can do the histogram, and roughly speaking, these two areas are the same. If I'd gone to a longer RNA hairpin, this area here would be much smaller. Now, if I go to a lower force, it's essentially pinned in the lower extension. It's completely folded. If I go to higher forces, it's pinned here. And therefore, this kind of looks like the experiments themselves. Brownian dynamic simulations, yeah. So I can go, in fact, we've done this to about nearly 0.1 seconds we followed this system. So that's the exact answer we know for the equilibrium free energy profile. Now we're going to attach the handles without the bead, because the bead relaxation, I argued, is not essential at this point, although we have come back to it later on. So the handles are described by standard polymer models. This is just the connectivity, the fact that the bead 1 and 2 are connected, 2 and 3 are connected, etc. And this is the bending rigidity term. So this value kappa A, Ka, determines how stiff my handle is. And in a simulation, I'm going to vary that to see what the effect of stiffness is on these free energy profiles and the kinetics. First, we want to characterize these handles. And we use Wormlike chain. We know the end-to-end distance distribution functions. From there, we can extract the persistence length. That we chose the monomer spacing here, B, between the two beads to be. This is completely irrelevant. And so at very low values of the bending rigidity, the LP is 0.6 nanometers. It's very tiny. I'm attaching a very flexible handle. At this value of the Ka, the persistence length is 70 nanometers, which is about 20 nanometers larger than DNA, therefore it's a stiff handles. So we have created on a computer a stiff and a flexible handle. We're going to do these computer simulations in exactly the same way as the experiments. We're going to apply a force here at this point, with this point being fixed. So there are few variables that you should be thinking about. One is the distance between these two endpoints. Sometimes I think I refer to that as a system coordinate. One is the molecular extension between the 3' and the 5' ends. That's this distance. And this is really what I want to know at the presence of force. And then there'll be a subscript or superscript 0, which tells you what the answers are in the absence of the handles and the beads, which is the exact answer. Okay? Applied, and so we're just going to do this exactly the same way. I think these are just merely the definitions. So the system just means this is molecular extension is the distance between the 3' and 5' ends. The system is the distance between Z at position P and Z at position O. And if the point that one wants to make is if measuring the system coordinate as a function of time reproduces faithfully the motion of this molecular extension, these two guys must be in complete phase with each other. That's what you expect. Otherwise, this guy is not faithfully reporting the dynamics of these two ends. And the first thing we want to show is that is indeed the case. If I look at the time as a function of system coordinate, I get a free energy profile which is coincident, which looks sort of the same as what I have in the absence of the handles, although there are quantitative differences. Here, this is meant to show that our model gives you behaviors which are not that different from DNA, except you have to worry about this. Okay. So the equilibrium properties of interest. So I'm going to construct a free energy profile, which, and only in this computer, I can separately measure what the distance between the molecular is with the handles attached and the molecules with the handles attached. In the experiments, I cannot do this in the first set of measurements, but here I can, and I also know what the exact answer are. So these are the three profiles that we're going to look at, and we'll see what the handle does to the three free energy profiles. Let's see. So this is the free energy profile. The black one is the exact answer. That's the one that's supposed to be 0. And the blue and the red, solid red, corresponds to the free energy profile that I get by monitoring only the system extension and the molecular extension. The first thing to notice is these two things coincide for this particular value of the ratio of the stiffness to the contour length. As I keep increasing the flexibility by increasing the contour length, I find deviations between the red and the blue curves. But they all differ from the black curves quantitatively. So short, stiff handles seem to give the best agreement between what the experimentalists would do, that's measure this, and what they really want to know, which is this. Okay? So if you want to know the accurate free energy profiles, you should attach stiff handles. Stiff handles means the ratio of the contour length to the persistence length should be a number which is of the order of 5 or 6 or something like that. But both of them distort the exact free energy, and so we have to worry about what the consequences of this distortion are. And remember, this is a very, very simple system, and if you can't get this right, we have to worry about this later on. Longer handles give us. And this shows you that if I took a very, very flexible handle, I get completely lousy results. So that's the first result that I want to show. Now, whenever I attach a handle, I basically also have transverse fluctuations. And the assumption that one makes in this experiment is that once I apply a force, the transverse fluctuations are very, very small. That means that the red guy here should be small, but this is not the case. But you want to minimize the transverse fluctuations, because if the transverse fluctuations are large, they will affect my free energy landscape and hence the free energy dynamics. And the minimal value turns out to be, it should be less than 10. The experimentalists typically use between 6 to 12. And so they are using as stiff a handle as they possibly can to get the free energy profiles. But these guys who do these experiments are absolutely terrific, top-notch guys. Okay. One can understand the whole thing that I'm telling you about using a toy model that you can teach in a classroom. So this toy model is exactly like my hairpin, the concept that I showed you, but it's simple to think about. And it is surprising that this has not been thought of before, and you could do this. So the way I'm going to construct this toy model is exactly the same way as the experiments and the simulations did. I have a handle, which is simply given by a Gaussian chain with a spacing b, and the length of the handle is just the product of number of monomers times b. That's contour length. Then I have another hairpin in between. Here, another Gaussian chain with a number of monomers being n0, and the spacing, which is a, different from b, another handle. And then I can apply force in this direction. The special thing about this particular middle region is, on this, I got to stop? No? There are two red balls, and if they're, Stop? Thank you, but I'm not. So the special thing about this, so if this thing didn't exist, I essentially have a Gaussian chain, and there's nothing interesting about it. I can solve the problem exactly, but even with this, we can solve the problem exactly. But there are two red balls at the end of this middle Gaussian chain, and when they are together, when the distance between them are less than some cutoff value that you specify, there's a bond in here of some specific energy. So it's essentially a garden variety Gaussian chain with one additional energy scale in the problem that tells you whether this bond between these red balls exists or not. When the bond between the red balls exists, we say that's folded, and if it's not, it's unfolded, and that's the two states that we're looking at. Okay? I think I've said everything here. I don't know why Greg made me 3 slides of the same thing, actually, but anyway. Okay, so this is an important slide. Now, I need to equate this Gaussian chain to something, map this on the Wormlike chain. You know that under tension, a Wormlike chain, the transverse fluctuation scale as 1 over after the 3 halves. This is calculable analytically, and 1 over square root of LP. A Gaussian chain, the transverse fluctuations in fact scale only as L times B. L is the contour length, and B is the spacing. So you can imagine a Gaussian chain to map onto the Wormlike chain by saying that the effective persistence line goes as 1 over B squared. So as you make the spacing between this Gaussian chain smaller, you're effectively making the handle stiffer and stiffer. So this is something that you should remember. That's how I'm going to map this toy model into a more realistic situation. So the energy function for this toy model is simple. This is just in the continuum representation. This is like sort of the Edwards-like representation. This is the handle, connectivity term, and then this is the connectivity term associated with the middle guy. This is the connectivity term with the end. This is the force that I'm applying on this, force times end-to-end distance. And this is the potential between these two red balls. And if the potential, if the distance between the red balls is less than some cutoff, it's harmonic. and otherwise it's this number here, and that's how I define its states. Okay, that's the energy function. So this is you can calculate everything analytically. In particular, you can calculate the probability of the extension being at some particular value of a particular value on the system coordinate, and hence the logarithm of this will be the free energy profile. And if you make this particular choice of parameter, it turns out this mimics the entire hairpin simulations that I showed you before. So everything that I told you in the case of simulations are reproduced here. This is the free energy profile as a function of system coordinate. And this is for a particular value of B, which means for a particular stiffness. And I'm increasing the length of the handles. And when the handle is 0, that's the exact answer. So you have a cusp because of a sharp cutoff potential. It turns out you can relax that by doing the calculation analytically. But so as you increase the handle length, I have deviations from this exact answer. At short handles, that this guy is the best. At the longest handles, the answer is horrible. And therefore, this tells you that you should choose stiff, short handles to get the exact answers as much as possible. Okay. And you can do the kinetics in this. So that's, so I'll come back to the kinetics of the model in a second. So the summary at this point is that stiff handles are required for good equilibrium free energy profiles that I found. What about the kinetics? Just like we defined 3 kinetics, free energy profiles, I can describe 3 hopping times. One is the exact answer. That's intrinsic unfolding folding rate, no handles, no beads. This is what I really want if I can get it. And the other is the system, the rates that you would get from the experimental measurement, which tells you what the z as a function of time is. And then the one where you get the rates by looking at the hopping distribution of first passage times associated with the extension alone. This one you can only get in a computer simulation. These two better coincide because otherwise you should throw out the experiments. And what is shown here, basically in more detail, I'll show I think in a second, is that this what happens. Let's see. So here is the folding time. There are four plots in here. One of them is the unfolding time at using the molecular extension. I better look at all these things. The other one, the one with no filled circle, is with the system coordinate, and the same thing for the folding time. So you can just look at everywhere you see open circle or open triangle. On top of that, there should be another curve which corresponds to the system. And if that's the case, we show that attaching the handles does not really screw up the folding times, and it happens everywhere. So if you attach the handles, it suffices, like an experiment, it suffices to measure the z as a function of time. Look at the first passage distributions. You'll get the answer exactly as though you were measuring the molecular extension. That's good news. But if your handle is stiffer, this is the exact answer. As you make the handle stiffer and stiffer, you'll see for stiff handles, the deviation from the exact answer keeps increasing. And in fact, you can make errors up to a factor of 10 to 100. 10 to 20 or so in the hopping rates by attaching very stiff handles. Admittedly, this factor of 10 to 20 is not like the 10 to the power of 100, 150 we heard in the last week, but 10 to 20, it makes a big difference in biology. Factor, you can compute why that should be the case. So stiff handles, in fact, don't give you a very good answer. But if I look at the corresponding results for the flexible handle, the deviation from the exact answer is much smaller. In fact, the largest deviation is about a factor of 3 or 4. So this says if you really want to get very accurate hopping rates, you should attach flexible handles. But if you want to get very accurate free energy profiles, you need to get stiff handles, right? Surely the experimentalist doesn't want to do that kind of experiment, with attaching 2 different kinds of handles. So handles of any type increases the folding and unfolding times. That's bad news. Stiffer handles change the times much more than flexible handles. The observed times are almost identical between the molecular extension and system coordinates. And therefore, experiments are still worth it, but we got to use some theory to figure out what's going on. So this is a hopping kinetics using So I'm not going to go into this too much because it's late in the day and who the hell wants to look at equations at this point. So the way we're going to do the kinetics, and this is a very complicated problem, it's not exactly soluble, is that when I unbind this and there's no bond existing and I want to calculate the refolding time, it's equivalent to calculating the rates of cyclization of an interior bond in this polymer, because that's all it can form, right? It's a rupture of this bond. So that's a cyclization kinetic, and that turns out even for a Gaussian chain is a very complicated problem, but we can make some progress. And this is the energy function in the continuum, and you use. I'm going to skip all this crap. I'll just show you this equation. We use something that's due to Wilhelmsky and Fixman. It relates a loop closure time to the folding time. You can write the propagators, compute them, blah, 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 blah. And it's good for students to work on all these things. And Sri and I did that a long time ago and got our PhDs and jobs. For the young kids should work 24 hours a day to figure out how to do these things. All you guys should do these sorts of calculations. So this is the folding rate as a function of handle normalized by the handle length equal to 0 for various values of B. And remember, B is stiffness. This is the stiffest, the least stiff, and these are the results from the hairpin simulations. What this shows is exactly what we found before, that if I take very flexible handles, which are these solid black, they deviate least from the exact answer, from ratio 1, whereas the stiff handles, you can screw up quite a bit, and that's exactly what I showed before, but this comes out of this almost analytic calculation of the time model. So these time models are useful for lots of purposes. Okay. Now, so far, everything I've said corresponds to what you do at the midpoint of the transition. But we want to make use of this measured, good free energy profile using stiff handles at other values of force. So how do you start doing that? We exploit the fact that even though both this quantity equilibrium free energy profile in the presence of handles deviates from this, and you can see the deviation, but it's not super terrible. And let's see what one can in fact make out of that. So what we're going to do is, it's tantamount to asking the following question: is extension neglecting the transverse fluctuation a very good reaction coordinate or not? That's what it boils down to. If it's a very good reaction coordinate, and this is a free energy profile, no handles, etc., etc., I can do the first passage time calculation for both going forward and backwards. The one thing I don't know is, and this is very hard problem, is effective diffusion coefficient. So we cheated in the beginning, and what we cheated was, and then we gave some dimensional argument why this is correct, that you take a value of force and calculate this, measure this quantity in a computer simulation and see what the du value is, and assume that doesn't depend too sensitively on force, which then you a priori check afterwards. We now have a little bit of a theory on how to get this for R as an extension coordinate. So the experimentalist, in this case of course is a computer experiment, has given us this free energy profile, which you obtain by attaching stiff handles. Then you say that the free energy profile at other values of force away from the midpoint is given by this equation. This is really the Bell model. It basically tilts the potential, this free energy profile, at other values of F. Once you're given the free energy profile, I do this double integral, which is basically the standard first passage time calculations. You know everything. You put an absorbing boundary condition here and here, and you know what the hopping rate is as a function of force, given only one piece of information which is measurable, namely the free energy profile at the midpoint of the transition for the system of interest. So the first thing you want to check is whether this ansatz is correct. After all, this is a model. So we can actually calculate this left-hand side of this quantity without having to make this assumption. But then we can make this assumption and see how good they are. And this is really meant to show you that, in fact, they coincide. You start from this and compute this, or you also compute this from computer simulation, then they basically coincide over a small range of force anyhow. Okay? So this ansatz is pretty good. Once the ansatz is pretty good, I can go back and calculate the hopping rates as a function of force. I'm only going from 13 to about 17 piconewtons. And the subscript KR and all those coincide basically, and therefore the expression, the analytic expression, by simply integrating those, doing the double integral for the first passage time, agrees with the simulated answer, thereby indicating for this problem extension is a reasonably good reaction coordinate. All you need is this particular piece of information that you can obtain either from experiments or by computer simulations by attaching fixed SIF handles and sitting at the midpoint of the transition. You can do this calculation very, very precisely for this toy model, and you do this for the toy model. The folding time and unfolding time, the solid lines, in fact, are analytic results. These are computer simulations obtained by the double integrals, and therefore you see that the Cramer's theory gives external agreement. It's not Cramer's theory; it's really first passage time calculation. Gives you a fantastic agreement experiment with the analytic calculation. This is. No, let me see what I want to. No, I'll make a few more. No, I'll make two more comments, and then I'm not going to talk about the Ribus switch. One of the things that I told you in the last hour was that if, depending upon the experiment that you do, the pathways of assembly can change quite a bit. Here is an example of that for the same RNA hairpin. You could do this experiment, and these are computer simulations, of hairpin formation by heating the hairpin to temperature above the melting temperature, quenching this, and allowing the hairpin to form, or you can unzip it and then quench the temperature, quench the force, and see what happens. The left-hand side here corresponds to the force, using force to unfold it, refolding the hairpin until the native state is formed, and there's a distribution of the folding times, and this green guy is a distribution of the looping time. So the picture that one has is you create an extended ensemble of extended molecules, then you have a bunch of unfolded conformations that form, and then the hairpin formation nucleates almost exclusively around the loop, and once this loop is nucleated, and the whole stack forms, and the hairpin is basically formed here. Okay, that's a mechanism that's obtained when you do the refold using force quench. If you do the same thing with the thermally unfolded ensemble, the nucleation in fact can sometimes, mostly it starts from the loop, but sometimes it can start from the middle, sometimes it can start from the end. Therefore, there are multiple routes to formation of this initial seed that in fact grows into this hairpin. Although these are all small systems, remember. So there are multiple routes from temperature quench, and this is the kind of experiments that Manfred Eigen did with his postdoc Porske in the 70s using temperature jump experiments, for which Eigen in fact won the Nobel Prize. And from those experiments we knew that the average folding time for a hairpin is about 1 to 10 microseconds, but in the presence of force, that number is stretched out by a factor of about 150 or so, and there is a structural explanation why this is the case. So this is two different experiments. The mechanism to form a very simple hairpin, it's a garden variety hairpin, nothing great about this. The mechanisms are totally different. So the probe that you use, in fact, will determine stuff. The last thing that I want to say, and I'm going to play 10-minute hooky here. I'm supposed to go till 5:30, but I'm going to stop after I say this. One of the great things about force, and this is really where the next level of inquiry that's going on, both not only in just looking monomeric folding, but things like unbinding of cell adhesion complexes, where people have discovered things like catch bonds and slip bonds and things of this kind, is the following. Just think about this kind of experiment that you might want to do it. So this doesn't matter what system you're actually looking at. I can actually do these experiments of force quench where I initiate folding the following way. I can first take the molecule in a low force state, apply a force such that it goes to some stretch state. over here. Right? And then I can re-quench this molecule. This is the midpoint of the transition, from the same stretched value of force to various low force values, which is less than Fm. Alternatively, I can go to various Fs values, initial stretched molecules, come back to the same Fq values, and these are asymmetric in the way you do the experiments. So if I now calculate various folding times, there's not a simple way in which you can scale the whole thing, but you can probe different parts of the energy landscape by merely doing the experiment differently. If you generically do those experiments by going to this force quench, for any system, it doesn't matter if it's a protein, globule, RNA, generically what you find is there's a long plateau when you quench the force, and it depends upon how fast this force is quenched, and only at later stages does the molecule know that it's a hairpin or a protein with a certain topology, etc., etc. So there are some universal aspects to this non-equilibrium type way of initiating folding that you can glean from this kind of experiments in which you do force protocol in a completely different way. People are doing these experiments, and there are theories that are out there that we and others have developed. So this will take me a long time to talk about the hairpin and the ribose switches, and I think I'm going to do this. So this is a conclusion for the next part. So the stiff handle should be used to study the folding landscape. Any handle will change the measured rates of folding, but flexible handles change the least, the toy model. But the most important lesson, and that's why these experiments are worth their weight in gold, gorgeous experiments, is that if you could measure this free energy profile of the system at the midpoint of the transition, then you can use first passage time formulation to obtain the hopping rates and the free energy profile at arbitrary value of force just from the single measurement, at least for hairpins, and we have also checked that this is the case for the so-called purine ribose switches. And one has to do many more calculations to figure out if these conclusions are general or not. So with that, I'll stop. Thanks a lot.
If people are trying to do some of these kinds of in more natural contexts, given that you'd expect all of these parameters to also change depending on whether your protein or RNA is embedded in a meshwork of some sort or is in the membrane. Are people trying to measure these quantities in, say, artificial membranes or embedded in meshworks?
Yep. There have been experiments on pulling out helices from bacterial rhodopsin, things absorbed on them, and anywhere literally that where people think they can use force, because there's many of the times if you integrate the force extension curve, you get the free energies very directly, and very often those are difficult to do in an ensemble experiment, which are easier to do here. The most notable example is nucleosome, where the interactions between the DNA and the histones is really not known extremely well, but with these force experiments, people have been able to do that. It's being used in all over the place, but in many situations, in fact, those are the things that we are interested in, but in a lot of them, there are these fundamental polymer type questions of how to make sense of the measurements, and for that you really need some sensible theories, and that's what we are after. That's one side, but we're also interested in structural interpretation of what's going on in these very complicated systems, like in our case nucleosome, and now more recently we've been interested in motility of kinesin tension.
But anyway, another way of asking that question may be the outlook for quantitative interpretation in more complex molecules is
very bright.
Bright?
Yes. Very bright, but it's not going to be easy, but it's very bright. I mean,
okay.
I think that if you just look at the way physicists or more quantitatively trained people get involved, single molecule is one place where the opportunities are greatest in terms of biophysics. There are, of course, things like bioinformatics, using languages of grammar, and lots of other things to do, other kinds of stuff, but most physicists don't know anything about that. but they can learn polymer stuff, they can learn soft matter, and then if you learn a little bit of the proteins and RNA and the complexes, you can in fact do a lot of interesting fundamental science applied with very, very interesting applications of biology. Very bright, I would say. But you really, in all these complicated problems, you really need to know what is the level of model that you really want, right? The natural tendency of many is to use some complicated all-atom simulations and then bang your head against what model for water, things like that. Well, that's not unimportant, but you really, you should keep the question in your mind. That's the key thing, and that's where people make errors. But once you know what the question is, the level of abstraction to make quantitative prediction will come to you.
You were mentioning these multiple routes in hairpin formation.
Yeah.
I was just wondering, how far is that a finite size effect? So if you make these strings really long?
Yeah. You still will have multiple routes. You can make them arbitrarily long, because then they branch into something else. But up to until 50 and things like that, this in fact happens actually. So, and you knew this even from, even though the Zimbrag has only 2 parameters, and you want to look at the molecular explanation of the nucleation and elongation of fructose, there are multiple routes present. And then it also depends upon the probe. In fact, when you do the force quench probe, the number of routes is restricted compared to temperature.
Yeah, this was interesting. Yeah.
You might have thought the opposite, all right. Yeah.
Thank you.
The stiffness of this handle in experiment?
What do you mean? The stiffness is given by LP, which is standard value.
Yeah, so that's one. But in your theory, when you are talking about changing the stiffness of the handle to have the hopping rates.
Yeah, but we wanted to see what range of LP values you can use to get reasonable values. Okay. In experiments, stiffness is fixed.
For a given either DNA or RNA, it's fixed. That's what.
Yeah.
And second question is that when you are changing the stiffness, so you have the unfolded states and the folded states.
Yeah.
Now these hopping rates, like when you are talking about the Kramer's problem, is it like stiffness equivalent to some barrier change in that Kramer's problem? I probably missed something there.
Yeah. So what is extracted is a free energy profile of the molecular extension for a given stiffness, and what is used only is the hairpin free energy profile. That's it. There's no handle there when you go to the mean first persistent calculation. The objective is, from the measurement, can you predict what's going on in the hopping kinetics? And that's a problem that I showed you. So the handles are used merely to obtain the free energy profile. After that, they are out of the theory.
How can we make sure that we're exactly stretching from the ends in the experiments?
Not a problem. Maybe I didn't explain this carefully. At the end of the handles, you put biotin, and then there's and your bead will be coated with streptavidin, and there's a very specific interaction that binds the biotin and the streptavidin. So you know you're binding the end to the bead.
It may be possible that we can stretch from the middle.
Say what?
Not from the end, from the middle we can do that. Can we do it from the middle?
Middle of what?
Middle of the
Use to explain
middle of the head pin.
I don't know what you're saying actually. You're saying, can I attach the handle to somewhere in the middle of the hairpin? Yes, that's possible. And that's an interesting question, is that what is the elasticity of the material, if the RNA or protein, if I change the pulling direction? That's basically what you're asking, instead of the ends. And in fact, I don't know, for the hairpin it's not been done. For GFP, the forces required to completely unfold GFP changes by a factor of 6 depending upon where you attach where you pull, and so the pathways in fact depend on where you attach it. Yeah. And that's been experimentally measured, and with Matthias Rief, and I have written a paper explaining the origins of that. And that very much depends upon the topology of the structure that you're looking at. So that's a good point. So the R being a good reaction coordinate will also depend on the direction along which you pull. In the case of laser optical tweezers, there are no experiments that I'm aware of where the pulling direction has been changed by attaching the handle to various parts. And that's something that's worth doing. But I got to tell you this, the experimentalists, and they have better things to do once they do the initial experiments like Carlos Bustamante or Steve Block. They're really interested in bigger questions on biology, and so they move on, right? It'll be up to some younger guy who's got nothing better to do, who wants to establish a name to clean up these things. And they're worth really cleaning up because it's an important question that you ask.
Yeah, so you mentioned that stiffer handles give you a more accurate free energy landscape, whereas flexible handles give you better rates.
Yeah, I didn't mention it, I showed that. Actually.
Yeah, you showed it, yeah. So if you do two independent experiments, one with stiffer handles and one with flexible handles, does it make sense to correlate the results of the two? I mean, say you measure the energy landscape with the stiff ones and the rates with the flexible ones.
Yeah.
But then can you actually make sensible or meaningful comparisons between the two experiments? Are they reliable, in other words?
No experimental in his right mind is going to do those kinds of experiments. Okay, I mean, think about these experiments. I mean, he's going to do only one experiment using stiff handles, and then you want to make sense out of the data, actually. Doing these additional experiments are really not so easy to do, because when you attach these flexible handles, if at all you can engineer them, they bring in lots of complications in the measurement process, and that's why they're best done either on a computer or in theory. Our overarching goal was to really make sense of the measurements, and therefore we wanted to explore the parameter space of the properties of the handles on the landscape and the kinetics, so that we have laid a proper theoretical framework to interpret this and other classes of experiments. And we're still in the process of doing so, incidentally, because of the hydrodynamic problems that I mentioned, as well as the fact that when you go to a complex landscape, we haven't fully still established, which means the experimentalist is also not fully established, whether the measured thing actually is intrinsic to the system of interest or not.
And a related sort of thing was that they used, the experiments were done with polystyrene beads, which typically have a surface charge.
No, not these. These don't have surface charges.
Oh, they don't?
No.
Okay.
No. You're thinking about these polyballs that colloid guys use in water, and this is not.
Okay.
Okay. Place to stop. Let's thank Dave Thirumalai again for a wonderful set of lectures.